But okay, let me start. So we know that there are big questions we kind of think about a lot. We know that we would like to learn how to compute in CFT and strong coupling. We know that we would like to understand exactly how quantum gravity works. And we know that we would like to understand how to resolve issues that we know black holes have in general relativity. So, and so for all of this, there's a pretty good kind of candidate of how to try to answer some of these questions, or a candidate that would potentially help to answer some of them. Part of it is just thinking about, for these two, for example, thinking about string theory in general. And for these two as well, one could also think about holography as well, maybe separate concept. And these things they tell us a lot about what we want to learn on these things, but there's still a lot we don't understand also in this setting. And we don't know, even if we think that strings may be a good quantum theory, are a good quantum theory of gravity, and even if we know how to use holography in many settings in order to compute stuff, we don't know exactly how to compute many things in string theory, and we don't know exactly why holography works or how it works. We don't know how it reacts. And so, in order to try to think about these questions kind of at a deeper level, one would think about doing what was done countless times in the history of physics, which is to consider a reasonably good toy model. So in a reasonably good toy model, we're gonna try to add more structures. Such as supersymmetry or conformal symmetry. Or maybe think about how many dimensions or degrees of freedom we want, etc. So we want to have more structure because that allows us to compute more stuff, but we also don't want to have too much structure, because when you have too much structure, then it becomes too simple, and the toy model doesn't capture really what we want to understand. So it doesn't have to be too simple. And I think kind of my motivation to work in this subject is that, in some sense, strings in AdS3 is exactly the sweet spot, or one of the sweet spots in that way of thinking. It's simple enough in the sense that we can do a lot of computation for it in this context, but it's complicated enough, and it retains, we think, a lot of features of the actual, of what happens in higher dimensions, for example, or how holography works, maybe more in general. And so the idea is to try to leverage as much as we can from this toy model. Okay, so just the idea of where does it come from? So first of all, it arises as a background in type 2B. When you think about compactifying on S1, which I usually denote with the letter Y, and for example, a T4. So T4 could be case 3, for example. It's not the only case, but there are a lot of situations which give the same or similar backgrounds in the near horizon. But if you go to the near horizon, then you get AdS3, where what I'm doing is I'm taking NS5 range, say N5, NS5 range. Sorry? It's just mean cosmic space. In the right. Sorry. One comma. And so say N5 NS5 range, wrapping the torus and the circle, and then I have also on top of this a number of fundamental strings wrapping DS1, say N1 fundamental string. So then, if you have that, you go to the near horizon, AdS3 geometry, which has the nice feature that it's only sourced by NS Flux. If you work in string frame, the size of the AdS3, so the radius of the AdS3 square in units of alpha prime, is N5, and the string coupling is basically N5 over N1 up to some C4 volume, which is kind of irrelevant here.
Put X2B and not any other.
I'm mostly going to be thinking about that, but of course, since I'm working in I'm going to do SQLity later. That's why I wrote it. But yes, this what I said here also applies to it. Yeah. It's not irrelevant, it's just that it's not the only compact thing that gives you near horizon AdS3. The actual details of the theory that you get, the details of the internal manifold, so that's gonna, all of this is gonna give some AdS3 times some 7-dimensional internal manifold. And I want to be mostly agnostic about what is going to be in the lectures, but there are several examples: T4, K3, also S3 times another S1. It's going to be there are several options. It's not irrelevant for depending on what you want to compute, but I'm mostly going to be agnostic about that. Yes. Okay. Yeah. I agree. Yes. Yeah. Yeah. I'm gonna. Of course, it's in here, and you have to take care that it's not making your dilaton blow up or anything. But yeah, I agree. Yeah. Of course. Okay. So fine. So the idea of one of the nice things, since we get a near horizon AdS3, is that this is one of the original instances of AdS3 already in the original paper by Malatena. And the kind of special thing about it is that, as opposed to what happens in other AdSs in other dimensions, this we really have a setting where we think about the sources as being only NSNS. And this, combined with the fact that AdS3 is a group manifold, a Lie group manifold, or more precisely, the universal covering of it. And this manifold is FL2R. Again, the universal covering of it. I get to the details of what that means in a bit. But the fact that it's pure NSNS and that the AdS3 is a group manifold guarantees that we have a well-defined worldsheet description. And that because this is a group manifold, it's in terms of a Wezumino-Witten model, what's known as a Wezumino-Witten model. I'm gonna write the actions and define all of this in a bit, but just for the introduction, bear with me. So this is a Wezumino-Witten model, and as kind of the usual compact Euclidean Wezumino-Witten model that we think about, we would like to think that this is exactly so long. And let me add a question mark here because the AdS3 case has a lot of interesting features that made this kind of idea vague for the last 20, let's say 20, almost 25 years. Because there are a lot of special things that happen here that kind of, even though we think it's exactly solvable, they kind of complicate the computation. And by exactly solvable, I mean that we can compute without using anything like perturbation theory. We can compute all the CFT data that we want, the spectrum, the OB coefficient, the 4-point correlation function, for example, etc. Fine. So beyond being the case where we can actually quantize and in principle solve the worldsheet theory exactly, there's also more structure that comes with it, with the fact because of the fact that the dual CFT is into D, lives into D, and as such has a Virasoro symmetry. And then we have a lot more structure also compared to what happens for CFTs in higher dimensions. For example, the n equals 4 being the n equals 4 pyramid, being the dual of AdS5 versus 5. And so, again, there's a lot more than usual we can compute here. And one question that also, it's also interesting because there are a lot of interesting applications of these things. So of course you know there are black hole applications. To name a few. The black hole applications. This was, for example, one of the first instances of the counting of microstates, the microscopic counting of the entropy of the black hole, as done by Strominger and Maffa. I guess in 96 and 97. And it also has, there's a lot to say about this. And one nice thing is that when I talk about black holes in AdS3, I'm talking about BTC black holes. And these BTC black holes, they have a kind of interesting feature, which again is only for the case of AdS3, which is that as a geometry, I can get them directly from AdS3 as some orbifold of AdS3, some global orbifold of AdS3. So this is just some identification of the coordinates in the usual sense. But the point of it is that many of what we can say about strings in AdS3 per se is going to also be useful to describe what happens with strings in this kind of backgrounds just because of this fact. And also this kind of, if I think about the dual picture, and I think about the 1D5 system, this is the, as we all know in this group, this is the kind of framework in which there are, on top of these results and a lot of results on black holes themselves, it's also the framework where a lot happens in the fastball program. A lot of the more explicit computations in the fastball program can be carried out. I hope this serves as a motivation to think that, kind of to believe that this is a nice thing to study. But there are kind of questions like I glossed over here. The more important one being, I know that there's a dual CFT in 2 dimensions, but one big question what we want to ask is which CFT2? Okay? And of course we know in AdS5 versus 5 is kind of simple because we look at the gauge theory on the branes, and the gauge theory is because of the amount of symmetry we have and so on. The gauge theory, and the fact that we are in 4 dimensions, the gauge theory is already conformal, but as it happens in AdS3, if we look in terms of the D1, D5 system, that's what I did this duality is kind of more natural to think about it in that way. The gauge theory description, for the low energy theory on the brains obviously is not conformal. Of course, we're not in 4 dimensions, so the gauge coupling is dimensionful. So this was found not to be the case. And so there's an important question here on exactly what is the CFT we're talking about, the CFT2 we're talking about. And we know that this theory is not conformal, but since when we go to the near horizon, AdS3, we get to an AdS geometry, it has to flow to a conformal fixed point. And there are kind of two basic things we can say from the get-go about this. We can say one, that it's going to have central charge going to be 6 N1 on N5. Actually, if we're talking about the T4 case, there's an extra +6 here. I'm gonna write once. It's a decoupled part of the theory. It doesn't kind of affect anything. And this is the last time I'm gonna worry about it. But you can just think about the space-time central charge being given by this formula. So it's just basically the product of the two charges that I have, the number of pi primes and the number of string-like objects, be it in either of the SQL pictures. And we also know from how much supersymmetry is actually preserved that it has to be an n equals 4,4 theory in 2D language. It has a lot of supersymmetry. Again, this is for T4. Yeah.
Do you need like a scaling limit for M1 and N5, or do you expect this to work for also small?
No. Okay. So if I want to have a weakly coupled description in the NS5 picture, I need to have N1 much larger than N5. So as Eric was saying, there's a factor of the T4 volume inside this equation, but let's just ignore it now.
And both large, or
Sorry?
both large, or only N1 large?
Right. So that's kind of part of what I'm going to take to talk about as we go along the lecture. N5 being large is not necessary. So the idea is that in order to have a well-defined worldsheet theory, in the sense that I think about the topological expansion, and again, along all these lectures, I'm really going to concentrate on the large n limit. And so what we would call the large n limit in general, so I'm always going to work at first order in the topological expansion. But the kind of nice thing, one of the very nice things about this model is that you don't need to require, because you have an exactly solvable worldsheet model, you don't need to require that the size of the curvature is very small. Even if you have large curvature, meaning even if your AdS space is string size or almost string size or even below string size, slightly below string size, which is also allowed, you can still work with the worldsheet model. Exactly. And actually, in the case of the T4, so in the compactification that gives you AdS3 cross S3 cross T4, the minimal value that's allowed is N5 equals 1. That corresponds to AdS3 being exactly string size. And that's part of what's been, of the recent developments on the subject. That's exactly what what's believed to be the dual of the symmetric orbital T. But I get to that.
But you can also describe N1 small, right?
With the worldsheet theory, in principle, I mean, it's going to be strongly coupled.
Yeah.
if you go to the SQL description, you can think you can work with supergravity, but you cannot use the worldsheet theory because you have Raman fluxes.
So can we compare this to the worldsheet central charge?
Yeah, I'm gonna get to that in a little bit. The worldsheet central charge is gonna basically be for the supersymmetric setting. Well, the worldsheet central charge is gonna be 0 always, right? I'm gonna quantize the worldsheet theory. I want to cancel the conformal anomaly, right? So if I think about the whole worldsheet theory, it's gonna be 0. If I think about only the AdS3 factor, the AdS3 part of the geometry, it's gonna be something like this. Okay. But I don't know if that answers the question. Yeah. Yeah. Yes. Yes. Exactly. Okay. Right. So beyond this, what can we say about the actual CFT2? Actually, thanks for the question, Johan. I should have said that from the beginning. The big point when I talk about exactly solvable is that you can go well beyond supergravity. So you don't need to have alpha prime small. Or which makes n5 large. Okay. And so if we think about the gauge theory description of the brain, again, we can think about the ones as being instantons in the D5 theory. As usual, the brain from the brains within brains, well-known paper. And the idea is that if we think about this object as being the kind of heavy objects that are present in the background, we want to think of the fixed point we're getting to as something describing the low energy dynamics of this object. And so the idea is that we're going to have to describe the fixed point should describe the IR dynamics of the slowly moving instanton. So how many instantons? A solution with n1 instantons. Again, solution is when I think about n1 instantons, but it's not n1 individual instantons, it's a solution which has instanton charge n1. And so if we think about, of course, when I mean slowly moving, I don't only mean slowly moving in space and time, I mean slowly moving in all the instanton moduli space that I can have. And so we would think that there is something we would call the instanton moduli space. And it's discussed in the, for example, in the paper by Strominger and Waffa, that this should have central charge 6, let me call it C1, have central charge 6 times n5. You can actually show it by thinking about by using the amount of supersymmetry that you have and thinking about this instanton solution. And if it was true that these n1 instances, these n1 D1 brains were non-interacting, just by the fact that they are indistinguishable from each other, you would end up with the conclusion that this theory is going to be some type of symmetrical group. By which I mean taking n1 copies of your theory and modding out by the permutation group. Okay, just because these things are all indistinguishable from each other, so you kind of, if it was true that they were not interacting with each other, it was just the sum of one instant on solutions, then this is the target space that you think about describing with your higher fixed points. But of course,
I don't understand why instantons. I thought the D1s were wrapping the S1, but then in time.
okay, sorry, Doc, I'm using the word, but it's just that that's what people call them usually in the literature. Yeah, exactly. Because these are defined, so we're talking about six-dimensional theory, the instantons are string-like objects, and that's exactly what it's talking about. But yes, thank you. But of course, saying this is wrong. These things interact with each other. So it's not true that the CFT has to be this CFT. At least so far, what people think is that this CFT, that the actual CFT2 that we're talking about should be some marginal deformation of this guy. There should be some deformation that moves around in the moduli space. At one point in moduli space, I have this is the moduli space, not the instanton moduli space, but the moduli space of the actual CFT2 that I'm trying to describe. There's going to be one point which is a symmetric orbifold, and there's going to be another point where I'm going to have my worldsheet theory, for example, which is where n5. I don't know. For example, if you want to think about some point in moduli space where you have a well-defined supergravity description, that's going to be for n5 large. And the question is, what is this point? What is this deformation? And do they ever coincide? Okay. And that's part of what we're going to go through.
There could be many worksheet points.
Yeah. Actually, if you want, I'm telling you to do it like this. I don't want to say. So if you fix some n5 and some n1, there's one worldsheet point. It's not going to be this one. Okay. This is the moduli space for this fixed central charge and 1 and 5. With this supersymmetry, if you fix one of those, it's going to be here. But in principle, yes, there's the whole. If you want, there's the whole. So what we're going to see. Or keeping the plot for later. Okay. If we want to see, is that actually there's a whole line of worldsheet theories in the sense of worldsheet theories that I can actually solve, which is called the NS locus. Okay. The whole infinite line, semi-infinite line, and it starts. Say if we're talking about the T4 case, it starts here. There's the symmetric orbifold point, and then it moves around here. Okay. And then there are a lot of other points which correspond to other points in the moduli space, talking about one-on-one fluxes and so on, which I don't know how to do the worldsheet theory. But they're part of the marginal deformation of that.
Can I just ask?
Yeah.
Is there some physical interpretation of the parameter along this red segment that you drew, which connects the symmetric orbit? Like, is it related to n1 and 5 or something like that? Is it some of the strength of the coupling between the instantons? Is that the idea? Or?
It's kind of, so that's kind of one of the things that's not usually nicely explained in literature. There's kind of a broad picture like this. I would say that it depends on if you want to think about moving both n1 and n5, or if you want to think about staying at fixed central charge and thinking about the moduli space of with that being fixed. If I think about that being fixed, then I can think about changing n1 and n5 in such a way that this doesn't change, and this corresponds to basically moving away from n5 equals 1. So if I grow n5, I go in this direction. Okay, but that's kind of a broad picture, and again, I'm gonna be much more precise when I get to the computation in a bit.
So if we stay in the same moduli space, it's like the space of continuous deformation. So we're given CFT, then probably n1 and 5 should stay fixed, right? Because n1 can only jump by a discrete amount.
Yeah. Again,
It's okay.
it's kind of
Understand better what's actually going on.
Oh, so on this line, that means you've got strong coupling points and weak coupling points, and because there's also like weak coupling is n1 greater than n5, but then if you're allowed to vary,
maybe let me be more precise when we get to
That's fine.
because this is a kind of a topic discussion. I don't want to do it just up in the air with the actual equation. No, that's true. Actually, yeah. In general, you will want to think of these things as quantized, as counting what you have, what the sources are in your background. But formally, for the worldsheet theory, anyway, you're gonna take and want to be very large, very large. Yes. 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 Yeah. Exactly. That's what I want to get to. That was my next point. So if I think in terms of a U duality of using some of the U duality I have available in string theory, I can go from a setting where I have n1 d1 and n5 d5 and covariantly transform my model into a model where I have n1 n5 d1 and 1 d5. In this case, the theory on the d5 is abelian, so it's much more tractable, and actually thinking about these kind of things makes more sense, and we can exactly pinpoint. I mean, it's very simple to say what the instant memory space ends up being, because it's only a single n5 now. And so in this case, the CFT2 associated to that would be some deformation of the symmetric orbit of big N on T4, because exactly central charge 6, because of the supersymmetry part. And where I'm taking N to be N1 and 5. Okay. That's what Eric was pointing. Okay, and maybe I should mention that this result of having a central charge here, what the central charge was for AdS3, the fact that you had the central charge in the asymptotic symmetries of your theory was derived a long time ago, well before AdS3, was by Brown and Hanel. I think in '86. Again, just by studying the asymptotic symmetry here. Wasting of time. Okay. So the kind of idea of the lectures is going to be to try to actually go and compute correlation functions in the worldsheet, study the spectrum, etc., compute the correlation functions in the worldsheet model, and try to pinpoint exactly what I mean by some deformation of some theory like this. Okay. So the plan, just before I go into the actual finishing introduction, the plan is gonna have roughly the first 3 lectures are going to be devoted to the, let's say, the Witten model of AdS3. And they're going to contain the geometric aspects, the spectrum, how you construct the space-time symmetries, from the worldsheet point of view, and how you think about correlation functions. How you actually go and compute them. And a big part of all of this, which would be simply wrong if I just gave a whole introduction on this subject and simply didn't mention it, big part of it is going to be spectral flow. Okay, spectral flow is one of the maybe infamous ingredients here. And the fact that there are spectrally flowed states, and I'm going to be precise about what I mean in a second, is kind of, and that we have to compute that they have, these are states that have strange properties from the CFT point of view, from the worldsheet CFT point of view, and that make the computation of their correlation function, for example, quite complicated. And so I'm going to try to go over that in some detail. Then the fourth lecture is going to be about holography. Well, the whole thing is going to be kind of related to holography, but the fourth lecture is going to be about thinking about what the holographic theory is. As I said, it's going to have 2 parts. One is going to be the tensionless strings, which is again part of the recent developments, and it's what I was referring to as the n5 equals 1 point, if you want. And then the question is the formation of the orbital. The symmetric orbital at n5 different from 1. Let's say larger than 1. This is a bit imprecise, but okay. And then the last lecture is going to be about applications. Part of it is going to be on black holes, and part of it is going to be about another application that I didn't mention so far, which is little string theory, which is a string but non-gravitational theory that you get to describe the theory on the NS5 branes themselves, and it's also related to CT bar deformation, the graphic theory. And I don't know if Monica is here online, but if she's going to tell me that this is not CT bar. So this is single trace CT bar. It's a different version of it. It has nice details and important differences, and we're going to hopefully get into that in detail. Okay, any questions before I actually start? Let me decide after here. I mean, if I can't separate the n into some n1 and n5. Yes. So I'm gonna get to the details of how you see these N1s and N5 from the worldsheet theory, but in particular from the worldsheet theory itself, what actually happens is that you kind of, if you say at large n, you're really only working at formally N1 being infinite, and you kind of see the finite N1 effects if you really think about the spacetime theory beyond the worldsheet theory on the sphere. But the N5 has a very precise role in the game. And so from the, at least in the NS5 picture, they're kind of clearly distinguished. I'm gonna be precise about exactly how and how they enter in the spectrum, the variation functions, and so on, and how you actually see that you need some N1 factor, even from the worldsheet theory, being some integer number. But and that may probably even going to come up today later. But kind of maybe let's see if when I get there precisely enough to answer your question, and if not, you can ask again. Yeah.
I'm just curious, will you mention sort of generalizations to other dimensions or things? Because from your introduction, it feels like everything has to come together right to have a WZW model and to be able to solve it and to go to the tensionless limit, et cetera, et cetera. And like one would wonder, okay, does that work for AdS5 process 5 or some theoretic setups or stuff like that?
So, okay. So the first disclaimer is I wasn't planning on talking about it. What I can say is that there is not much known about how to generalize it beyond that. There's kind of, so there are I'm going to talk about this kind of long string states and the role they play in this game and so on. There is an idea that these kind of things are, so when you think about AdS5, for example, they're related to the what people call the giant gravitons in AdS5, kind of things. There are some kind of links. The only precise statement, and I'm not sure how, I haven't gone through all the details of the paper. I can only tell you what they say they do. But the kind of more precise statement is on the level of AdS5 process 5 in a paper by Gavardir and Gopakumar. Well, what they did is they claim that the generalization of this NS and duality at N5 equals 1 being the symmetric orbifold of P4. They claim that the generalization of that, so at this very special point, which let's say is the tensionless point where you have higher spin modes, and the theory becomes free in some sense. So okay, this is S3 equals P4. So the generalization to the AdS5 case in the tensionless regime which again is when the AdS space becomes very small, is dual to, so you can think about this as being, about the worldsheet theory here as being part of as being the super Wezomino-Witten model on this GS1,1/2, right, which captures the symmetries and the supersymmetries of your background, the DS3 background. So here they kind of think about it as in terms of the PSU 2,2/4, right? And they say that this is free and equal for super infinite, right? I think the check is at the level of the spectrum, and you can do similar things in the sense that here instead of having one spectral flow, you have two different spectral flows, kind of, but the physics is more or less similar. And you can show some, you can kind of match the spectrum here with the spectrum of the free theory, with the operators of the free theory. But this is it's a very special point. It's much more special than in AdS3 because at this point you can actually have a worldsheet description in terms of free fields only because it's a very particular limit, and when you go away from that, you can't do it. Just go to supergraphic. But I mean, we can discuss about it, but it's not that I know much, but I wasn't going to go into that.
When you're saying free and equal 4, you mean 0 cap and constant?
0 cap. Okay. Any other questions? Anyway, I'm already behind schedule, obviously. We'll get where we get. Okay. So let me start with the geometry, with, let's say, geodesics. First part, geodesics in global. AdS3. It's important when we're talking about global AdS3 as opposed to Poincaré AdS3. Global AdS3, you can define it as the Lorentzian hyperboloid from an equation like this. So the usual deal. All the radius squared. And it has basically looks like a cylinder where I'm gonna use coordinate t here at the time. I'm gonna use some circular coordinate y, and then the radial one is gonna be called rho. And it's kind of important that this is global AdS3 because I want to be talking about, if I want to think about it in holographic terms, I want to be talking about the actual NS vacuum of the holographic theory. That means that I want to preserve the full SL2R times SL2R symmetries, the full conformal, full SL2R conformal SL2R symmetries, and there are several ways to see that this is actually the manifold you should think about, the background you should think about. So for example, if you think about the fermions, one night, well, first of all, the boundary is a cylinder. That's the first clue. The second clue is that when you the circle you're working on, when you go to the center of AdS, it becomes contractible, and so you can think about going around the circle as just a simple Lorentz rotation around the origin, and that means that the fermions have to be antiperiodic. Okay, and that tells you that if you take your boundary theory on the cylinder and you take the fermions to be antiperiodic, then it has to be the NS sector. And another way to see it is that if you compare with Poincaré AdS3, so you think about the mass or the energy of this guy. It's the energy of Poincaré AdS3, meaning the massless UTD black hole, minus C over 12 for this C, the C that was the central charge of the holographic theory. That again tells you that if you take this as being your zero, your reference, then the NS vacuum is exactly minus C over 12 below that. But kind of maybe the best point about why it should be exactly global AdS3 is that the geometry is something like this. Where y is identity track by y. with 2 pi, y equals 2 pi, and and this is exactly the same as I was saying, the SL2R group manifold, which just try that use of notation. This is isomorphic to SU1, 1, and I'm gonna use it to parameterize the elements of this group as follows. This is e to the I b sigma 3. Sigmas are the Pauli matrices. E to the rho sigma 1 and e to the I u sigma 3, where p and u are p plus minus y.
This G is in SU 1, 1, right? No.
Yes. This is here. These two are isomorphic. And to be precise, if you think about SL2R, the group manifold itself, actually the time direction should also be compact. But if you go to the universal cover, so you just decompactify it, you get global AdS3. That's what people usually denote as a hat here. From now on, I'm going to forget about this hat, and whenever I say SL2R, I'm going to mean the universal cover of the SL2R. Let me just set up the notation. You can see easily that from these group elements, you can derive this metric. And you can see this by just looking at the kinetic term on the sigma model, which is something like this. I have a factor here, sorry, which I'm going to call it k. And because of the fact that I'm going to talk about throughout the lectures from now on, I'm going to use bosonic notation just because it's kind of simpler and it contains all the features I want to talk about. But what roughly happens is that from the supersymmetric setting, I have this N5, and this I have to identify it with k minus 2, k plus k minus 2. Anyway, if I'm thinking about a large N5 or large K setting where I'm talking about supergravity, for example, supergravity regime where this is large enough, N5 is just K. So that's the meaning of this K here. As I was saying, N5 or K is the thing that tells you what the size of your AdS space is. And the kinetic part of the sigma model on this group manifold just has all the usual action. Right, like this. Where I'm going to use, for example, at some point that sigma plus minus. So this is tau and sigma plus minus. I'm going to call it tau plus minus sigma. And if you take this formula here, you say that these guys are fields of tau and sigma. The v, the u, and the rho are fields of tau and sigma. You take this group element, you plug it here, you go through the computation, you just get back this metric here as in the sense of the usual sense of worldsheet things here, you get the metric, let's say something like this. Right, the metric that you get in the kinetic term is exactly the AdS3 metric. With this parameterization, it's exactly this coordinates here. However, I need to add one more ingredient to the game, which is that I told you that this AdS3 was supported by an SNS flux, right? And so I need to add one more term to the action, which tells me what that H flux is or what the D flux is, and that comes like it's called the well-to-minnow action, which just, of course, I'm obviously going to get the numbers wrong here, but I think this looks something like before. And it's just defined on some three-dimensional manifold such that the boundary of this M3 is this sigma 2, the worldsheet. And you can just write it like this in form notation. It's this cubed. Okay.
And this works for any worldsheet metric. I mean, the indices alpha has to be raised with a eta or a delta, or you can have any.
Well, I'm writing it here as a flat metric, but you can do it more than.
You took Lorentz English on the worldsheet.
Yes, so far yes. But I want to. So when I get to the Euclidean model, I'm gonna take everything Euclidean. But when I'm in the Lorentzian setting, I'm trying to do everything Lorentzian. So there's some discussion about what I mean when I talk about energy and so on. This gives you, if you think about what this gives you, in this case, because I'm going to have some H3, the NSNS flux, which is D of some D. So this I can integrate by parts, and it gives me something that looks like this. Where the B field is exactly what you get in the gravity solution, which is something like K pinch squared rho dt dy. So again, this was we knew, I didn't write it, but we knew that this was the flux according to this AdS3. If you plug this parameterization in here, you get exactly this stuff. Okay.
So you resumindo defined on the non-compact manifolds.
Yeah.
K not necessarily arbitrary. It's not necessarily efficient.
Yes, exactly. Here, okay. So there are two parts of what you're saying. The first part is I went over the details here, but when I say I'm having some M3 here, I have to define some way in which I extend the G to the three-dimensional guy. If you are in the compact case, you can show that the difference between choosing two different M3s here gives if you change that, you change the action by 2 pi times k. And so for this model to be invariant, k has to be an integer. But that's true for compact manifold. But global AdS3 is not a compact manifold, and so in general, k doesn't have to be an integer number. It is an integer number in the AdS3 cross S3 cross T4 case. Because in that case, you have to, when you look at the worldsheet here, you have to balance, so roughly the size of the S3 and the size of the AdS3 have to be the same in order to have supersymmetry, and then that means that the k has to be the number of primes on the S3, so it has to be the N5 inside the S3. So in that case, it is still an integer number, even though AdS3 is non-compact, but in general, you're right, k doesn't have to be an integer number. So, yes. Because okay, so I just wanted to set up the notation. Any questions here?
So, what's globally non-defined in the B field?
No, in this case it's fine. It's just that in general you could have situations where H is not exact. H is close, but it's not exactly exact. It's not exact, and you cannot write it directly in this way. then you cannot integrate by parts here. But in this case, it's fine.
You're assuming n1 is equal to 0.
Okay, in this case, locally, it's fine. That's true. Yeah, you're right. You're absolutely right.
Understand if the conclusion was that only k is only integer k are allowed, or also non-integer k are allowed?
R instead of Z.
So I had a teacher once that used to say, everything I write on the blackboard, you have to take the exact opposite of it. That's probably going to be true for me. Yeah, you're absolutely right, Mike. Thank you for the clarification. This is a local state.
You have already started.
Well, I was writing. It was a very silent lecture. I thought everyone would enjoy a bit of quiet, which is fine. Okay. Okay. So I'm gonna take my Witten action, the pull action, which is gonna be just the sum of these two pieces I defined, the kinetic term and the Wessel-Minor term. And since this k is up here, I can think about it as being inversely proportional to the, let's say, square of the coupling constant, if you want. And so that means that the classical limit of the model is going to be at large k going to infinity, which is okay with our intuition, of course, because that means that the AdS is large and I have a nice supergravity description. The symmetry of the model is that I can take its SL2 R left times SL2 R right. Means that I can take my element G and plug in two elements here, where G L and G R are part of SL2 R. And for this, as Grisha was saying, for this particular choice of coefficients, it turns out that the equations of motion look like this. So normally I would have something with this term plus something with this term, and only some combination would be 0. For this choice of coefficient, it turns out that both terms vanish separately. Well, one of them vanishes and then implies the other. So it's just a very simple looking system of equations of motion. And the result from this is that you get two conserved currents, which look like this. Which are the trace of the generators of the algebra times each of these. For this TA of the generators. And so, because of this fact that these two things are zero separately, it turns out that these currents here depend only on sigma plus in one case and only on sigma minus on the other case. And there's a part of the symmetry is gauged, and I get this that can be an arbitrary, can have an arbitrary dependent on sigma plus, and this one on sigma minus. So this is local. If I think about these currents as in terms of their modes, integrating the different Fourier modes on the circle, I get the following algebra. So again, I'm going to use the Pauli matrices, and I'm going to define the ladder operators as the usual way, sigma 1 plus minus I sigma 2. In my parameterization, so you get something like this. This is minus k over 2. And you all know probably this, but it's just about setting up the notation. Plus m minus m in minus 2j n plus m 3 plus k n plus m 0. So this is the affine FM2 R. And then I obviously have the same with the anti-holomorphic sector, but holomorphic when I go to complex notation, but the other sector. And you'll notice that when I go to the classical limit, then what happens is that all the modes that have non-zero zero index, they become extremely heavy to generate. And so in the classical limit from this, I just keep the zero modes. And then what happens when this is the precise combination of coefficients is that you can use the Sugawara construction to show that this is actually a conformal theory. So it's classically conformal kind of trivially, but at the quantum level, you need to have this correct relative coefficient between these two guys. And the idea is that you, from the generators of the algebra themselves, you can build your energy momentum tensor, conserved energy momentum tensor. And for example, that looks like this. For example, the T++ component, which usually called just T, and it's the holomorphic one in complex notation, looks like this. This sign is the Lorentzian part of the story. And you also see This guy that the value you're asking about, it also kind of appears everywhere. Whenever you see it, you can think about it as a quantum correction because the classical limit is k large. And this is what, when you go to the supersymmetric case, makes everything beautiful because you reabsorb that shift and you just get n5 everywhere. And from this, you get the usual modes, the Virasoro mode. And I'm gonna try to use the usual L for the worldsheet ones and the different letters for the spacetime ones. The usual thing. And they act on the current well. But again, this is in every book out there, in particular the yellow one. But just to set up the notation, and this central charge here is the worldsheet central charge, and as Silvan was asking, this ends up being 3k over k minus 2. So again, you get a quantum correction here. Okay. And finally, you can define the vertex operator. Anyway, I want to set up the notation. I'm going to go back to the geodesics and the geometry in a second, but just to know what we're talking about. You can define the vertex operator. Let's call them B, J, M. So the J and the M play a very similar role as what they do in the usual SP2 theory. J is going to be the spin, and M is going to be the projection. So this, when I put it at 0 at the origin in complex notation, this gives you in the vacuum, this gives you some state Jm, and when I act on that, I have that this is primary if all the positive modes annihilate the state, which automatically implies that all the Virasoro positive modes, because they are built from the currents themselves, also annihilate the state. This is primary. And this is going to be kind of an important point. Seems an easy statement, but it's going to be an important point for us because the converse statement is not true. If you have a Virasoro primary, it doesn't need to be an affine primary, and that's where spectrally flowed states are going to live. That's why they are kind of special. Spectrally flowed states are going to be states that satisfy this condition, but not this one. So let's write it like this. Okay.
So it's not a physical state condition.
No, this is a physical state condition.
Yeah.
So what happens? This is what is usually so in the canonical treatment of Weissman-Witten models, you always start with these objects because they are the affine primaries, and you know that they have to be then Virasoro primaries, and usually that's good enough. But for the SF2R case, it's not true. For SU2, for example, this gives you everything you need.
Is it related to the fact for SU2 you have representation that has lowest weight? Because this seems like we're thinking about representation.
Well, here you're going to have both. You're going to have representations which are not highest weight, but you're also going to have representations which are highest weight or lowest weight.
But what do you say difference between SU2 and SL2? The fact that my question is more, you're saying the difference between SL2 and SU2? For SL2, Virasoro does not imply.
No, in general, Virasoro never implies.
True, but for combat, it's cool. You're saying
for combat, what's happening is that if you look at the state, it gives you a consistent spectrum for your CFT already.
So for no compact, there is some additional state which are primary, but not primary.
Yeah. I don't know about general non-compact, but for AdS3. Okay, and the last thing I want to say is that maybe I can write it here. Is that just from the fact that you have that your construction for the energy momentum tensor is a Sugawara construction, you can show that you have a null state, which is just this. So this acting on any state is going to give you 0 because of the definition of the L-1 is exactly this guy. Okay. But if you think about it more generally, this gives you a differential equation for the correlation function, because I can think of this guy. I'm sorry, and I should have said here that the JA0 after JM with the sum generator of the representation. So matrix 1, for example, minus here, depending on your convention. And so this implies that correlation functions satisfy an equation like this. I'm writing in representation here, but it's the usual. So this has to be 0.
So why is k minus 2 in the denominator now?
Because it's a k minus 2 here.
Yeah, but k minus 2 was in the second term, and now dz is L minus 1, right?
Yeah, sorry, I should be here. Yes, thank you. And the only kind of reason there are 2 reasons I'm writing this, just to say that in general, this might be enough to solve for the 4-point functions of your model. For example, in the SU2 case, or in the SUN case in general, you can solve exactly for the 4-point function just by using generically all the constraints that you have here from the symmetry, and in particular this one. And I probably have minus here. But one comment that's going to be useful for me is that, again, if you look at the classical limit, which is k going to infinity, this term disappears, and this tells you that classically the correction function has to be independent of the worldsheet coordinates. Okay.
What happens for k equals to 2?
That's where that's where you shouldn't go. The theory becomes non-unitary. I don't know. So beyond it becomes non-unitary. Okay, exactly what to do. I don't know exactly. There is some particular subtlety, but that's kind of the hard cutoff. Wait, so. Fine. Anyway, this is all known stuff. So now let me go to the thing I wanted to say, is that if we go for the geometry, if you look at the metric on the base field I have, this current here, the global 0 mode, these guys, correspond to the global symmetries of the symmetries of your model, and in particular they correspond to the 3 killing vectors that this maximally supersymmetric space has. And in this case, in particular, the J3 0 corresponds to some killing vector. And so if I say that in particular I have J03 acting on some state which gives me the eigenvalue, then from the fact that the Killing vector for J03 is dt minus is basically proportional to dt minus dy, and this one is proportional to dt plus dy. In the original global AdS3 coordinates again. So this is t, and this is y. So this shows that you can identify the energy as being 1/2 here. The energy as being m plus bar, and the momentum on the circle as being m. Well, I put it as m bar minus m. Okay. So I'm gonna want to think, whenever I think about m and m bar, I want to think about eigenvalues such that this thing ends up being, these two things end up being real. Okay. So if you, in terms of the actual coordinates, you can show that you can just compute what the currents are. So now I want to study the geodesics, the classical geodesics. And for this, I just have to find some solution, which is some g. The classical solution to the equations of motion is simply taking something like this. Okay, you factorize this to the holomorphic and anti-holomorphic. I keep using the word holomorphic and anti-holomorphic, but I mean sigma plus and sigma minus. This automatically solves the equations of motion that I wrote before. It's very easy to see. And so, if I get one classical solution, it's also defined up to conjugation by a matrix here and something. But the main point I will say is I want to study the geodesics here. I want to study 3 types of geodesics. So first, I'm going to start with the very simple ones. The most simple ones you can think of, which are one time-like and one space-like. Which is simply taking G to be e to the p alpha tau, which I can write as the e the I alpha sigma plus sigma minus over 2. And sigma 3 here. Okay. And so you see that this just says that the only thing that's happening is that t is alpha tau. Okay, that's all there is. And so in this case, you have, let me just prepare a bit. This is just this. The rho is 0, and the y is, well, it's not exactly well defined at that point. It's just some particle going like this in the center of AdS. And I call it a particle because of the fact that this is independent of sigma, right? So there's no worldsheet I'm going around, so there's no kind of string I'm thinking about. It's just a line here.
I think I missed something important. So if we restrict to the state, if you're in this representation, we restrict to the states which are annihilated by all the positive k's. So positive. What is the representation of SL2R that we get? Is it a finite dimension representation or
no? No, the SL2R representations, the global, the zero mode, are not finite.
What is the small j? The small j mean?
The j labels the Casimir. you have a Casimir which is roughly like the SU2 one. So instead of being j plus 1, it's minus j minus 1. I'm going to write that in a second, but they're not finite dimensional.
Is it a discrete series or the principal series for SO2?
I'm going to get to that in a second. Kind of that. The goal of the today is getting to that. This is one of the discrete ones. Anything that is bound inside AdS and doesn't reach the boundary is going to be one of the discrete ones.
So J is a positive integer for these ones.
It's not an integer. It's positive, but it's not an integer. We'll see what it has to be. Okay. And so in this case, if you actually compute the energy momentum tensor, you get something like this. Again, computing just means you take your definition, you plug this G into this definition here, you compute the current, you plug that in here, and you see what you get. But there's no big, I mean, I'm not trying to skip important computations, it's just a simple one. And on the other hand, I have a space-like one, which is basically this. Now sigma 1, okay, which means that again I can write it as e to the I sigma plus sigma minus over 2 sigma 1, which gives me rho being alpha tau and y being 0 and c being 0. Okay?
Sigma plus minus sigma minus. Is that exponent?
Sorry?
Sigma plus minus sigma minus.
I define them as tau plus minus. So this is tau. Maybe, I don't know if it's the usual definition. Okay, and so this is simply something doing this. Okay, it just moves in the radial direction, and that's it. That's a very simple. Now, the problem is that when you want to define things in AdS3 across some internal path, such that the combination of the two has to have total matter central charge being 26. But otherwise, I'm just going to be agnostic about what this guy is. I'm just going to say it has the right central charge and that it's compact. Then it means that you should impose the Virasoro condition, right? So the actual physical states only appear when you impose the Virasoro condition on the worldsheet. That means that the total worldsheet energy momentum tensor has to vanish. And this is what I call just T, which is the AdS part, plus the internal part. Okay? And if I think about some primary in the internal part, I'm just going to take this to be H internal. Okay, it's just the eigenvalue of L0. I have to ask that this is 0. And since this is a Euclidean compact CFT, this guy H int has to be positive. Okay? Is it too low here? So what happens is that, okay, this one is perfectly fine, right? Because I plug this minus k alpha squared over 4. This is negative. I plug it here. I put it on the other side. I solve. I get alpha in terms of the internal weight, and that's it. But if I try to do the same here, if you compute what the energy momentum tensor is, it's plus k alpha over 4. Okay, so there's no physical solution associated with this guy, which is what we would have expected because it's a space-like geodesic.
Nico?
Yeah.
I missed where was K positive being? Like, because before we said like, well, K can be anything, and
I'm always going to take it
Now
to
you're
be,
using the fact
take it to be k larger than 2.
yeah, because of what Grisha was asking about that's the hard. Yeah, okay, thank you.
But in general, the action when you wrote the original action should be positive because action should be positive.
Yeah.
Just by positive definiteness of the action.
Exactly.
Yeah, so -0, 2 is weird, but it's
Yeah, 0, 2 is one of the, well, 0, 2 is what we heard yesterday in Hong Kong.
yeah, right. The non-critical.
0, 2 is the non-critical strings. Where you get less than 10 dimensions, etc. Okay. So far so good? Yeah. Okay, now I want to look at the slightly more general geodesics. So 2, I can always get another solution by just multiplying on the left and on the right with some constant. Right? That's still going to be a solution because it's still going to be factored in the dependencies in the holomorphic, in the worldsheet coordinate. So what I do is I take T to H plus T, so let's call this J0. So I take a solution which is this guy. Okay, I'm gonna use for the first case, for the time-like, I'm going to use H plus equals H minus inverse equal what? Put the inverse here, equal e to the 1/2 rho sigma 1, and for the space like I'm gonna use H plus H minus being e to the 1/2 rho 0 sigma 2. Okay. And I think it's kind of pointless to derive the equations themselves, but derive what happens in the solution is better if I just plot what this does. So this, for the space like one, what it does is it takes this and it adds some radial momentum, right? Some radial dependence, and it does something like this. Okay. So this is a shifted, well, the conjugated time like one. And for the space like one, it's a bit less interesting. And the kind of maximal radius you get to is this R0 in the transformation, in the conjugation. And the other one just gives something like this, which I don't have much to say because it's a very interesting part. It has some radial dependence. It has some time dependence. Okay. And now I want to think about a third step, which is the first time I'm going to say spectral flow. So, kind of, if you wanted to just have an idea of what spectral flow is, and then you were good to go. I think this is the kind of the important part of the talk, even though this is just the classical version. Is the fact that you also get new solutions if you just take your G and you move to something like this. And I'm going to add some parameter omega plus and some parameter omega minus here. Okay? And it is still a solution simply because of the fact that it's still factorized. Right? I just have sigma plus here and sigma minus here. So this is still a solution. It's a new solution. And if you look at the parameterization I gave at the beginning, what it does is it takes t, the original whatever t was, for example, this t which was alpha tau, to the original t plus omega plus omega minus over 2 tau plus minus sigma, and it takes y is equal to y plus exactly the opposite. Okay, that's what it does. As already here, you see that if these guys are not the same, I have a problem because this is the compact direction on the worldsheet. And so if this is here for a non-trivial coefficient, I'm going to have closed time-like curves, I think. Right, I'm going to go back to the same point. And then this means that I need to set this to 0, so I need to set this to be the same. And from now on, I'll only call it omega. And also, now this is not here anymore. I have it here, I just have omega here, and because y is also periodically identified, I need omega to be integral value. Okay? Fine. And now we look at what this does. So let me maybe draw the picture first, and then look at what it does to the algebra.
So the previous two, or whatever number of classical solutions you constructed could be interpreted as points particles. Here you really need like a string.
Right, exactly. So that's one of the first comments, is that since I add this sigma here, right, now I do the geodesic I'm describing does depend on both tau and sigma, and so when it's a string geodesic, right? It's a string moving in AdS3. It's not just a point particle. And that's exactly what happens. Just because I take y to y plus omega sigma, what happens is that this, I need another color, is that this just, well, it kind of stretches it a bit as well, but that's not good because I also add the omega tau in t, right? But let's forget for a second about that. What it does is it creates some string that does this. Okay? So it's a string. This one is bound inside AdS, but it's a string that's kind of pulsating around the origin. But the more interesting part is here. Yes, I can just erase it. It's more simple enough. Anyway, not particularly useful. Is that, and as I'm going to show in a second, what happens is that even if you started with a space-like one, you end up with something where you can solve the Virasoro condition after the spectrum flow. So before you couldn't, but afterwards, I'm going to show it in a second in the equations, but now you can solve it. So now it's not anymore some unphysical thing. And if you look at what it does, precisely it brings, I can show you the actual dependence of the coordinates. It's easy to write, but not particularly instructive. What it does is it takes some string which goes at tau going to infinity, it goes to t going to infinity, and the rho goes to the boundary, right? The rho goes to infinity, then it goes through the center of AdS, and then it goes back here, and it's a string that does this. So it's something like this. Okay. Okay. So these are what are called the short strings. and these are what are called the long string solutions. And in terms of what you were asking, Daniel, these are the discrete representations with vector flow, and these are the continuous representations with vector.
Just to understand the picture, is this thing rotating or it's static? Because naturally, well, I don't know. If it's in the picture to the left, I would say you have a thing which just rotates around center of AdS.
So when you, for example, if I only have shown omega equals 1, this is something that was when you go once around in sigma, you go once around the y circle. This rotation here is the sigma part.
The string doesn't rotate, it just
No, the string is not rotated, it's just pulsate. Yeah. Alright. Yeah. Yeah. See why not? I never really tried, but I don't see why not. I mean, the short answer is I don't know, but I've never seen it used for anything. I don't see an obvious obstruction. Yeah. So in general, what you do is you think about what it does in AdS3, and you also have some movement in the, say, S3 part, for example, and that's what you include when you have your, the duals of the chiral primaries and so on. It's part of the game for sure. But so here I'm not really kind of caring too much about the details of the internal part. I'm just saying that there is some internal manifold with the right properties, but I don't know if I have anything useful to say about. You had something in mind? Yes, definitely. Yeah. I would have to think a bit about it. Again, I don't see an obvious obstruction, but I never really tried.
The short strings, their envelope are the geodesics of before.
Yes.
But for the long string, it's not the case.
It's not the case. Yeah.
And how is it? So what's the? There's no interface.
Well, the envelope is not. It's not also. It's not the same. That's what I said, because you also you take even in the short string you take t to t plus omega tau. But it's not true that this is moving exactly at the same way. It's just a way to. But it also kind of stretches in this direction.
They all oscillate at the same frequency, the short strings.
Oscillate not the same
frequency. The period is always 2 pi, maybe. Just like for massive particles in AdS.
No. The frequency always is given by this original alpha here. So you can that depends on what the internal weight is. It's not always the same. I mean, if the actual solution.
I thought that if you just take massive particles in AdS, in this global AdS, they always oscillate the same frequency, right?
Let me look at it. I can. Okay, let me go back to that in a bit. Look at the actual. I don't have them written here. In principle. Sorry?
What was the question? Well, if you take a massive particle, you start with a massive particle. If you have AdS, you give it some momentum. It's gonna start going towards the boundary, and then it will start coming back, and it will come back to the center of AdS after some time, and it will just keep going. It's like a kind of an oscillator, not exactly a harmonic oscillator. There's some period of these oscillations, and I thought this was supposed to be the same, like independently of the momentum that you give initially, but maybe that's not true.
We We can look at the actual solutions.
If you unify it, it's work is massive then. You can't go all the way to the market.
Okay, so the point when you do this, you can see what happens at the algebraic level, or you can see what happens with the currents, and what happens that this zero solution, but you take your J, you take it to your J, let's say the odd one, you take it to something that looks like this. Okay, over this. So this is by tilde I mean the solution before doing the spectral flow. Okay, and I want to keep the kind of usual symbol for the actual physical eigenvalue of current of the spectrally flowed configuration. So this is what it does. I can do it with the full set of things. I don't need to do it at the classical level. And J plus minus, they go into J plus minus equals to the plus minus I omega sigma plus minus. Okay, and so this is just if you look at the modes, this is just an automorphism of the algebra. Just brings the algebra into itself. It doesn't change any of the commutation relations. The modes of the G tildes are the same, have the same algebra, the same as the modes of the G's. And if you go through the Sugawara construction, and you look at what this does to the construction of the energy momentum tensor itself, you see that it gives you a new T, which is the old one minus omega J3 minus K. So here I need to put the fine. It gives you this. Okay. That's just simple algebraic exercise, and but there's something interesting about this is that I can relate the J tilde. I can relate it with the new J3. Right? This J3 is the guy that defines the energy of my configuration, as I said at the beginning. And since it appears here, I can think about I can compute directly, instead of just looking at the computing J3 itself and computing the energy, I can just solve the Virasoro condition and solve for this guy and see what the energy is in terms of the old variable, right? So that means that I can derive the energy, so the Virasoro, the total, which has to be 0, now looks like plus or minus K over 4 alpha squared, which were the two solutions I had before, minus omega J3, and I can put this on the other side. So I get J3 without the tilde and plus K omega squared plus the internal weight. Okay, this is the thing that has to be 0. Again, just be careful, this is kind of annoying, but I changed the sign here by changing from J to J tilde using this equation. Okay, fine. And here you see that you get extra contributions that allow you to solve the Virasoro condition, even if you started with something that was positive, right? And so they are both physical states. If you solve this for this guy is what we were calling M, if you want, on the solution, and you see that you get two behaviors. So for short strings and for long strings, The formula for the energy looks the following. I get something that looks like this. By the way, this factor here, I derived it for the first solution, but it doesn't change if I add the row 0 here. So the old t part doesn't care if there was a row 0 here, so it doesn't appear. Even in this situation where I had to put it to get a string, it doesn't appear in this formula. And the solution becomes like this. So again, this by E, I just mean now I'm assuming that. Let me assume that I'm working with states where J3 is the same as J3 bar. Okay, so then I solve here for J3, and this is just 2 J3, right? And so I get something like this. While here, obviously, I get something like this. Because I just changed the sign of the alpha squared term. Okay? And now you see that the energy of the short string is bounded above, right? If I take this, the smallest possible alpha, which is 0, alpha squared, which is 0, then this has an upper bound, which is okay, this guy. And here you see that you have exactly the opposite. There's a lower bound on the energy for the long string. So said another way, you need the threshold, you need to go above some energy to create a long string. You cannot create it already at very, very small energy. And one interesting thing that happens is that, so first of all, the bound is the same. So when you go to the maximal energy in the short string, you go to the minimal energy of the long string. So that tells you that there are configurations for which you can start with and this is going to show up in the variation functions. You can have interactions of short strings, which then unbound from the center of AdS and become long string configurations and just escape to the boundary. Because at this, if you give them enough energy, they produce something with enough energy, they end up being in the long string sector. And there's a particularly nice solution where this happens, which is if you take h int being a very particular value, which is k over 4 omega squared, right? If you take this guy, then in both cases here, the solution tells you that you can just set alpha to 0, right? Because this let's say it. You can solve say okay, let me go back to that. Anyway, the main point for this is that this gives you a solution where you can take alpha to 0, but the short string solution at this point, when you take h internal being k omega squared over 4, that if you look at the actual solutions for the target space field, they look exactly the same. Right? There's a value of h for which these two types of solution, when you start from one side and you start from the other, they get exactly the same form. So these two solutions are the same. And they take a very special value, which is just having y being omega sigma, b being omega tau, and rho being constant. Okay, so that's just one string staying at a fixed radius and just moving up, and that's it. So this solution just looks like this. Okay. And this again, the fact that these two things meet at some common solution reinforces what I was saying, that one can become the other. Okay. And I guess this would be a good place to stop. This also thing. Yeah, let's stop here.
Could you again the top why is this H special? This value K of 4 omega 4 square. What's special about this value so that we have the same solution for both regimes?
Yes, let me go back to that.
H was the scaling dimension in the internal CFT in the compact management?
Yes, exactly. Well, first of all, it's special because it's the only point where these two things the actual configuration is the same.
Well, it is kind of confusing because I would say that so you have both images basically change sign of alpha square, one goes to the other.
Yeah.
That's how I would say that if I do continuation in alpha square, I will interpolate it into
There's a very simple argument I am not remembering right now, which tells you that at this value, you can set alpha equals 0. And what from the you see from the original solution, the general that alpha basically sets your rate, it's rated the radial moment, and so this is the only value for which you can set alpha equals 0, and then it's the only thing that describes the static string. It's just moved. And it's special because it's the value at which, if you want, so why can this happen? This can happen because you have a gravitational attraction and you have a repulsion from the field. And this is the particular value where these two things exactly compensate. That's the main point. I'm going to remember this.
This can be reached by spectral flow from a point. Because if I take alpha equals 0 in the first solutions, it's kind of the limit where the particle doesn't.
Yeah, you have to take the limit carefully. It's kind of a funny limit.
In principle, that's the idea. It's an infinitely slow particle, and it's spectral flow, and you get this.
Yeah.
I guess by construction here, you've exhausted all possible. I mean, with the strings having both like.
Yeah, I haven't shown it.
Case, like this is a complete description of the spectrum.
I haven't shown it, and I'm going to talk much more about the spectrum in the next lecture. It's kind of easier to analyze it directly in the Euclidean setting. I'm going to talk about normalizability and so on. But yes, so all of this, of course, I should have said this is from this whole discussion is from the Maldacena Oguri paper, the first one from 2000. And yeah, they show explicitly that like everything else is just conjugations of this. So you kind of have all the geodesics you can have.
But what about this configuration which I was referring to, like rotative string? What's the solution to this?
Yeah, I don't think there's a big.
You were thinking yourself to the solutions for which is py equal to 0, right?
Yes, exactly. That's the choice I made here. Yeah, of course. I tried to do it kind of as intuitive as possible, but it's not. Once you allow for this to be non-zero, you get. But I only restricted to that when I computed the formula for the energy. That before, so for the actual solution, they were.
When you say everything is created by conjugation to one of those, conjugation you mean H plus equals H minus.
I mean some conjugation with some constant matrix, basically. Which could be different on one side. But there, I mean, it's gonna get more complicated, but there are no new features.
Yeah.
So at this point, I can think of this spectral flow as just kind of an organizing principle for the set of solutions where you have, first of all, the specific form.
Yeah.
But also because of the usual spectral flow rules, you know exactly how the energies
Exactly.
change. Right?
Yeah.
Put things in these families.
Yeah.
Okay.
Yeah, but so far it's just a way of getting to the string geodetics, showing that they're there, and that I think the main point of this story is that even if you start from a particle configuration which was not physical, you get something that is physical, and that's the ground string sector, and that's what for a long time, well, not for a long, that was for some time at the beginning of the story, before the Malasana-Wiri paper, people didn't really know exactly how to fit into the whole Wasserman-Witten description. But at the level of geodetics, it was kind of clear.
I have last. It's probably a very stupid question. But so in this context, it's not. Is the word spectral flow appropriate because it's really quantized? You cannot. Like it's quantized by this omega.
It's going to be quantized. It's algebraically.
Yeah. So it's a flow, but it's that's a flow. I said it was stupid.
Actually, I was looking yesterday around 2 a.m. when I couldn't sleep. I was trying to find the origin of the name spectral flow, and I couldn't. So maybe someone knows it.
Yeah, it's buried in a set of circularly referenced papers that some of which are not published, right? Where, but I think it goes back to Schwimmer and Seiberg.
Yeah, right. So there's a famous cyber paper which looks at this on the just for like compact settings, which is like S2 and so on, just the algebra that appear when you think about R-symmetries. So he's looking at the extended supersymmetries, CFT2 extended supersymmetries, and there, I think the main point, and that's what I'm going to show next time, is that here it really creates new states. Whereas if you are in the compact case, it just reshuffles what you call, well, in the Wasserman-Witten language, it reshuffles what you call primaries and descendants and so on. It does a mess, but there's nothing new, just a big mixing. Whereas here, it's really, really new solution. And you see it just because you can solve the Piazzetta condition for cases where you could.
Should we think of this spectral flow parameter as a label of irreducible representations of this affine SO2R somehow, or not really?
Of this?
Affine SO2R.
Affine SO2R. Yes. So okay, I'm gonna get to that, but basically the full spectrum of the model is gonna be given by. So first of all, you at omega equals 0, there's a discrete parameter which is this omega. At omega equals 0, you only have discrete states because what you would call the kind of the other ones are space-like. And I'm gonna show it explicitly. You can show that the states that are associated to the continuous sector when you have no spectral flow, they're just tachyonic, and you want to avoid them. And by tachyonic, I mean, I don't mean negative mass, I mean below the BF bound. And then when you go to the spectrally flowed sectors, you have a whole tower of both flowed discrete states and flowed continuous states. And that's going to define the whole spectrum of the model. But So it was, so before the Malesson-Anguli paper, it was discussed several times that if you don't add these states, the spectrum of the model as a CFT, if you try to think about it in, for example, in holographic terms, it just doesn't make sense because the energies you can achieve are just too small. I'm pointing to the wrong formula because omega equals 0 is not the right limit here, but you also have a bound for the, it's just a bit more complicated, longer to derive because you have to go through the currents themselves on the solution, but there's a bound on the energy. The energy is going to be related to the weight in the dual theory, and you have a, if you don't include the spectral flow, you just have an unphysically low bound on that. You basically are looking at the holographic theory, which has central charge proportional to N1 and N5, and your bound was something proportional to just N5. So it doesn't make sense to not have states above. Yeah.
Thank you again.